So in the last lecture we met this concept of spectral analysis in computer science. So this idea, we have a matrix, we have a scalar value, we have a vector, and when we multiply the matrix by the vector, the result is exactly the same as multiplying the vector by the scalar value. So the vector is what we call an eigenvector, and the scalar value an eigenvalue of that matrix. One thing I didn't talk about, however, was how do we compute these objects? If we're given an arbitrary matrix, how do we discover what its eigenvalues are and what its eigenvectors are? So this is a topic I'm going to be addressing in this lecture. So we saw we had this notion of dominance for eigenvalues, and we also saw it was possible for the eigenvalues of a matrix, since they arise as roots of a polynomial, these eigenvalues can be complex numbers. However, it's very often the case that we don't need every single eigenvalue for the matrix we've been given. Sometimes we are only interested in the dominant eigenvalue if there is one. So you'll recall that the dominant eigenvalue is the largest eigenvalue, but largest in the sense that its size is strictly bigger than any other eigenvalue for that matrix. So in many applications, we're only interested in the dominant eigenvalue, or even not so much that, but just the largest eigenvalue. In many cases, we're not really that interested in complex eigenvalues. We wish to have instances in which there are only real eigenvalues. So I mentioned this famous result called the Perron-Frobenius theorem. And one of its major contributions is this gives sufficient conditions on a real matrix that guarantee that that matrix has a positive real largest eigenvalue. This isn't necessarily a dominant, a unique largest value, however. But one thing these conditions guarantee is the existence of eigenvectors for that positive real eigenvalue, and these eigenvectors contain only positive real components. So what are the Perron-Frobenius conditions? To start off with, they apply to a matrix which only contains non-negative real numbers. The matrix also has to satisfy a condition of what's being called irreducible. I'm not going to define that in detail. I'll give some examples of matrices that we see in computing contexts which are guaranteed to be irreducible. So if our matrix has this property, if it contains only non-negative real numbers and is irreducible, what the Perron-Frobenius conditions guarantee is that that matrix has a unique positive real eigenvalue associated with it. Now, unique in this sense does not imply that that eigenvalue is dominant. It merely means there is a single real constant value which is positive and an eigenvalue of that matrix. Now this given eigenvalue, this unique positive real eigenvalue, this has with it an associated eigenvector that contains only positive real elements. So the non-negative real elements in the matrix, irreducibility of the matrix, that guarantees this condition and this condition. If we take any other eigenvalue associated with such a matrix, and this is including complex number values, all of these satisfy that their size is less than or equal to the size of this Perron-Frobenius eigenvalue. Now, what I mean by irreducibility, the technical definition is given in the course book. However, the important computer science case is if we look at the adjacency matrix of a graph which is strongly connected, then that matrix is irreducible. What do I mean by strongly connected? A directed graph is strongly connected if from any node in that graph we can follow a path of links to any other node in the graph. So how do we construct eigenvalues and eigenvectors if we're given a matrix of only real elements? Well, one very commonly used technique is called the power method. This is quite a simple algorithm. So where do we start from? We're going to assume that our given matrix does indeed have a dominant eigenvalue, a unique largest eigenvalue. And what the power method does is this allows us to construct an eigenvector which is associated with that value. And what this relies on is the fact that if we know a particular vector is an eigenvector for a given constant for that matrix, then if we take any real constant, if we multiply our known eigenvector by that constant, then the result is also an eigenvector with respect to that value. So what do we do in the power method? To start off with, we choose some initial guess. So very common choice is to choose the vector which consists entirely of ones. So that's our initial guess. We then set our starting point and we compute the result of multiplying our matrix by our current vector. And that gives us our next vector to look at. We increase the point we reached in the computation, and then we return to this step until our value has exceeded some maximum, some limit that we're using. So this specific value, this is a user-defined component. Now there are some problems with the power method. These aren't concerned with how quickly it converges towards a dominant eigenvector. The problem is that very quickly, after half a dozen iterations, the numbers that we are using become extremely large. They could have 10, 20 digits or more, and therefore what we find is the computation time involved increases. Now, it's quite an easy problem to overcome. There's a method we can use, which is called scaling. And what the power method with scaling does is it adds one additional step. We take and this step is added after the fourth step, and all we do, we take our current vector and we divide each component of that vector by the largest value in that vector itself. This is the absolute value that we're using. Now, this doesn't affect the result because all we are doing is we are replacing our current vector with a constant scalar multiple of itself. And by adding this step, this ensures that the numbers we are dealing with don't become too large, that they remain fairly small throughout the computation process. Now, that describes a technique for computing an eigenvector. What do we want to compute an eigenvalue, though? Well, this is even easier, really. We use a relationship which is referred to as a Rayleigh quotient. What does this do? We know how to find an approximation to a dominant eigenvector. And we can use this idea of Rayleigh quotient to find an associated eigenvalue for those vectors. So suppose we've used, for example, the power method to find an approximation to an eigenvector. What the Rayleigh quotient does is it computes this constant value. We take our matrix, we multiply it by the vector we've just found, and we compute the scalar product, the dot product of that vector with the transpose of that vector. And we divide the outcome by this scalar value, the scalar product of our vector with itself. So just to remind everyone what we call the dot product, this is the result of summing the component-wise multiplication of the two vector parts. So this computation for the Rayleigh product, this uses a dot product, and this reports the eigenvalue for the vector that we've just discovered. Suppose we're interested in other cases. We can find the smallest eigenvalue of a given matrix if that matrix is non-singular. How do we do that? All we need to do is observe that if lambda is our largest eigenvalue of a matrix, then the smallest eigenvalue of the inverse matrix is 1 divided by lambda. In other words, the smallest eigenvalue of our starting matrix A is 1 divided by the largest eigenvalue of the inverse matrix of A. So this is why we need this condition of non-singularity. We have other techniques, which again, these are described in the textbook, called the inverse power method and this technique called deflation, and these allow us to extract other eigenvalues once we've found the largest eigenvalue. There is a very complicated algorithm which allows us to find all real eigenvalues in the special case of symmetric matrices. I'm not going to describe that one. In practice, we don't actually have to worry too much about developing algorithms from scratch to uncover eigenvalues, because many programming languages, Python and Java, these have supporting numerical packages which actually carry out the process of computing eigenvalues and eigenvectors when given a particular matrix. This is even in the case where those eigenvalues are complex numbers. So where do we find other eigenvalues occurring? in the two computational applications that we're going to be looking at in the final two lectures, the first of those only uses a dominant eigenvalue and a related eigenvector. The second case uses a technique which can take any matrix at all and express that matrix as a product of three matrices which only have real eigenvalues. So the first application I'm going to be looking at is Google's page ranking algorithm. The second one uses a quite sophisticated technique called singular value decomposition. And this arises when we are trying to extract information from large data pools. So this is one of the areas in data science. It is also a very important technique in machine learning. I'm going to be looking at its use as a means of carrying out image compression. There was a very old traditional area of computer science which is called spectral graph theory, and this is looking at the relation between matrix spectra and properties of the graphs themselves. So this is a very old study in the area of algorithms and in computer science. So one very famous result from this area is, suppose we are trying to color the nodes of a graph in such a way that no two nodes which are joined by a link are given the same color. Then what we can show is that the number of colors we need is at most the largest eigenvalue plus 1. This is for the adjacency matrix of the graph, and it's at least this quantity here. Okay. So spectral graph theory allows us to give bounds on the number of colors we need to color the nodes of a graph. Another famous result is that the number of links in any graph is exactly this quantity here. We sum over all of the eigenvalues for the adjacency matrix, the result of squaring that eigenvalue and then dividing the outcome by 2. So let me just summarize what we've seen. Spectral analysis of graphs, networks, matrices and table structures, this is becoming increasingly important in modern computer science. It's been widely used as an approach to what are called ranking problems, where we're looking for the best ordering of some collections of results. And this has been used in web pages. This is what the Google search algorithm does. It's been used in predictive ordering of sports leagues. In other words, trying to forecast in what order teams will finish in a league. It's been used in a recent area of research in this department called argument strength. It's a very important technique generally, spectral analysis in machine learning and in data science. It's led to quite deep results in graph algorithms and in the field which you'll meet in the final year of the course called computational game theory. What I'm going to look at in the next lecture is one of its most significant successes, and that is in the search algorithm that Google uses to order results. So that's the topic we're going to be looking at next as an application of spectral methods.